Ladies and gentlemen, night owls and cosmic wanderers, welcome back to the Midnight Museum, where every episode opens a door into something strange, beautiful, and just a little unsettling. Tonight, that door may be more literal than usual. Imagine looking through a perfectly round window, suspended in empty space. On this side, Earth, the moon, and the familiar stars. On the other side, not darkness, but another sky. Perhaps a sky 10,000 light years away. Perhaps another galaxy. Perhaps another time. You take one step forward, cross a throat no longer than a hallway, and emerge somewhere light itself would need millennia to reach.
It is one of the most seductive ideas physics has ever given science fiction. The wormhole. A shortcut not merely through space, but through space-time.
And recently, the headlines have become bolder. Researchers model wormhole shadows. Quantum computers appear to send information through simulated wormholes. Physicists publish papers with phrases like humanly traversable. So tonight, we have to ask the question people actually care about. Have we finally found a real wormhole?
The short answer is no. No telescope has confirmed one. No laboratory has created a tunnel through physical space. But the long answer is much more interesting. Because wormholes are not fantasy pasted onto physics. They are possible geometries inside Einstein's theory of gravity. The mathematics allows us to describe them. Whether nature builds them, whether they remain open, and whether anything can survive the trip are three very different questions.
So we are not booking tickets tonight.
Not unless your travel insurance covers exotic matter, tidal gravity, and possible violations of causality.
Then settle in. We are going to trace the wormhole from Einstein's equations to black hole interiors, from negative energy to time machines, and from a 9-qubit experiment to the signals astronomers would actually search for. By the end, we will know what a wormhole is, what it is not, what a traveler might experience, and what evidence would justify the words, "We found one." Ready, Dr. Sam?
Let's take the shortcut.
A shortcut through space-time. Let's begin without equations. What is a wormhole in plain language?
Start with two places that are far apart in ordinary space. If you travel the normal route, you follow the space between them. A wormhole changes the geometry so that a second, much shorter route connects those locations. People often use the folded paper demonstration. Mark two dots on a sheet, fold the sheet until the dots touch, and push a pencil through. It is useful, but it can also mislead us, because the paper is being bent through a higher dimension that we can see. A real wormhole does not necessarily need to bulge into some visible outside dimension. In general relativity, space and time possess their own geometry. The shortcut can be described from within that geometry.
And the two ends are called mouths?
Yes, two mouths, joined by an interior region called the throat. If it is traversable, something can enter one mouth, pass through the throat, and emerge from the other. The distance through the wormhole can be short, even when the distance outside is enormous. But that does not mean you locally outrun light. Inside your immediate neighborhood, you still move slower than light. The trick is that the path itself is shorter.
That sounds like physics finding a loophole in its own speed limit.
A geometric loophole, perhaps, but not automatically a legal one. Einstein's field equations relate the curvature of space-time to matter and energy. They do not give us a single universe. They allow many possible space-time geometries. Some contain expanding universes. Some contain black holes. Some contain connections we call wormholes. An allowed solution is not proof that nature has manufactured the thing. I can write equations describing a perfectly frictionless machine. That does not mean one is waiting in a warehouse.
So when people say wormholes are predicted by relativity, the precise statement is that relativity permits certain wormhole-like solutions.
Exactly. And even then, we must ask whether the solution is stable. whether it can form, whether it requires impossible material, whether quantum effects destroy it, and whether a traveler can cross before it collapses. The word wormhole covers several related objects. The famous Einstein and Rosen bridge is not the same as the friendly doorway in a movie. A microscopic quantum connection is not the same as a human passage. A simulated holographic wormhole on a processor is not a puncture in the laboratory wall.
That distinction may be the theme of the episode. The mathematics can be real, even when the tunnel is not physically present.
Yes, and that is not a disappointment. Mathematical possibilities tell us where our theories bend, where they break, and what the universe would have to do to surprise us.
Einstein and Rosen build a bridge. The story starts in 1935 with Albert Einstein and Nathan Rosen. Were they trying to invent interstellar travel?
Not at all. They were wrestling with a problem in fundamental physics. General relativity described gravity magnificently, but some solutions contained singularities, places where the mathematics appeared to become pathological. Einstein and Rosen explored a construction that joined two sheets of spacetime at a narrow bridge. Their goal was connected to modeling particles without treating them as point singularities. The term wormhole came later, associated with John Wheeler.
What would their bridge look like?
Imagine the maximally extended geometry associated with an idealized, eternal Schwarzschild black hole. The mathematics contains two exterior regions connected through an interior bridge. On a spatial diagram, it resembles two funnels joined at their narrow ends. That is the Einstein-Rosen bridge. It is a foundational image, but it has a fatal problem for travelers. It pinches off too quickly. No signal can cross from one exterior region to the other.
So the original wormhole is non-traversable. You can draw the connection, but you cannot use it.
Correct. And the horizon matters. A black hole event horizon is a one-way causal boundary. Cross it, and every future-directed path leads deeper inward. NASA is very explicit on this point. Observed astrophysical black holes are not known portals or shortcuts. The romantic idea that every black hole is an entrance and every white hole an exit is not supported by observation.
If I approached one of the mouths in the Einstein-Rosen picture, could I at least see the other side?
The ordinary travel story fails before that question becomes useful. The global geometry does not provide a stable corridor linking the two exteriors. Depending on the idealized diagram, the bridge exists as a spatial relation at an instant, but it is not open long enough for light or matter to complete the crossing. In relativity, a picture of space at one moment can hide the causal structure. That is why physicists use space-time diagrams, not only folded paper pictures.
A bridge that exists yet cannot be crossed. That feels almost mythological.
It does, and it teaches an important lesson. Geometry alone is not enough. A usable wormhole must remain open, must lack a lethal horizon across the route, and must keep tidal forces within survivable limits. Once physicists began asking those engineering-style questions, wormholes moved from an elegant curiosity to a serious thought experiment.
Which brings us to Kip Thorne and a science fiction request.
Exactly. Sometimes fiction asks physics a question that physics did not realize it wanted to answer.
The traversable wormhole problem. In the 1980s, Carl Sagan was working on the novel Contact. He wanted a scientifically respectable method for rapid interstellar travel, and he consulted physicist Kip Thorne. That conversation helped inspire detailed work on traversable wormholes. What changed?
Michael Morris and Kip Thorne treated a wormhole almost like a design problem. Suppose we demand a spherical passage with no event horizon blocking the way. Suppose the throat stays open. Suppose the traveler does not encounter crushing tidal forces. What geometry would satisfy those requirements? And what kind of stress energy would support it? Their 1988 work gave physicists a clean framework for asking those questions.
What does traversable require?
First, the throat must not collapse before the traveler crosses. Second, there should be no event horizon, preventing two-way communication. Third, gravitational acceleration at the mouths should be manageable. Fourth, the difference in gravity between the traveler's head and feet, the tidal force, should not tear the traveler apart. Fifth, the transit time should be reasonable, both for the traveler and for observers waiting outside.
A surprisingly demanding building code.
Spacetime inspectors are strict. A small throat tends to create enormous curvature and tidal stress. A larger, gently curved throat could in principle be more comfortable. But supporting a large throat dramatically increases the physical challenge. The wormhole must flare outward at its narrowest point rather than simply closing. In ordinary general relativity, that flaring geometry requires unusual stress energy.
If the ideal wormhole were somehow stable, what would entering it feel like? Would there be a hard surface?
Not necessarily. A well-designed traversable wormhole could have no material doorway and no sharp boundary. You might see a distorted spherical view of the destination hanging ahead of you. Light from the far region would travel through the throat, so the mouth could act like a window with extreme gravitational lensing. As you approached, the view might wrap around your field of vision. Stars could appear in multiple images, stretched into arcs and rings. If tidal forces were controlled, crossing the throat might feel uneventful locally. No bump, no flash, just a changing sky.
That is somehow more eerie than a glowing portal.
Because space-time would not announce the boundary. The dramatic effects would be optical and global. But this gentle journey assumes the very thing we do not know how to provide: a structure that holds the throat open.
And the bill for that structure is paid in exotic matter.
That is where the dream meets the energy conditions.
Exotic matter and negative energy. The phrase exotic matter sounds like a mysterious substance locked in a government vault. What does it mean here?
In wormhole discussions, it usually does not mean antimatter, dark matter, or an undiscovered element. It means a distribution of stress and energy that behaves unlike ordinary matter and violates an energy condition used in relativity. The key one is often the null energy condition. Roughly speaking, ordinary matter seen along a light-like path has non-negative energy density. A traversable wormhole throat generally needs that condition to be violated.
In simpler terms, the geometry wants something like negative energy to push the throat apart.
That is the common shorthand. Ordinary positive energy gravitates in the familiar, attractive way. The wormhole's throat needs a kind of gravitational support that prevents it from pinching shut. Some quantum systems can produce regions where the measured energy density is below the vacuum reference level. The Casimir effect is often mentioned. Place conducting boundaries very close together, alter the allowed quantum field modes, and the energy between the plates can be lower than outside.
So nature does allow negative energy. Problem solved?
Not remotely. The existence of small, constrained quantum negative energy effects does not mean we can collect a barrel of negative mass and reinforce a starship-sized throat. Quantum field theory places severe restrictions on how negative the energy can be, how long it can last, and how it is balanced by positive energy. These are often discussed through quantum inequalities. The amounts and configurations used in convenient traversable wormhole models are far beyond anything we know how to produce.
So the issue is not only whether negative energy can occur, but whether enough of the right kind can be arranged in the right place for long enough.
Precisely. And different theories change the accounting. Modified gravity models, extra dimensions, quantum effects, or unusual fields may permit wormhole solutions with different requirements. In 2021, for example, researchers described humanly traversable solutions within a theory involving an extra-dimensional Randall-Sundrum framework. That title attracted attention, but it did not mean someone had found a construction plan using established standard model materials. It showed that under particular beyond standard model assumptions, the equations can admit a comfortable passage.
And other work pushes in the opposite direction.
Yes, a 2022 analysis by Daniel Turno argued that standard spherically symmetric traversable wormholes are incompatible with C-masculine gravity under the conditions studied. That is not the final word on every imaginable geometry or theory, but it illustrates how demanding consistency becomes when quantum fields and dynamical formation are included. A static picture may look beautiful. The moment you ask how it forms and survives, the object can disappear.
The wormhole keeps moving into deeper physics. General relativity opens the door, quantum theory stands in the doorway, and neither theory alone tells us the complete story.
Exactly. Wormholes live at the fault line between gravity and quantum mechanics. That is one reason physicists keep studying them, even without evidence that cosmic civilizations are commuting through them.
Would the journey be survivable? Let's grant ourselves one miracle. Somewhere near Earth, a stable mouth appears, large enough for a spacecraft. Mission Control asks Dr. Sam whether we should enter. What do you check first?
I would begin with the gravitational field around the mouth. Does it act like an enormous compact mass? Is there an accretion disk of superheated gas? Are nearby stars or spacecraft being violently lensed or accelerated? A wormhole need not mimic a black hole in every model, but strong curvature can make the neighborhood hazardous.
Then radiation?
Absolutely. Light and particles can be gravitationally blue-shifted as they fall into a deep potential. Radiation entering from both mouths might accumulate or become extremely energetic depending on the geometry. Some theoretical analyses find instabilities in which small disturbances grow. A tunnel that is calm in an exact equation may react badly to the first photon, dust grain, or spacecraft that enters it. Back reaction matters. The traveler is not merely observing space-time. The traveler carries energy and therefore changes space-time.
Could the ship itself cause the throat to collapse?
In some models, yes. If the supporting negative energy is delicate, the positive energy of the spacecraft could alter the balance. That is one of those details science fiction understandably skips. A door strong enough to remain open when empty may fail when a massive object crosses.
Suppose it stays open. What happens to the people inside?
We calculate tidal acceleration across the body or ship. Near a small, sharply curved throat, different parts of you could be pulled in different directions. The same basic spaghettification problem associated with compact black holes. Morris and Thorne deliberately considered conditions in which the tidal acceleration would be no greater than something comparable to Earth gravity. A sufficiently large and carefully shaped throat could make the passage locally comfortable.
What would we see looking backward?
You might see the entrance universe compressed into a bright, distorted region behind you, while the destination expands ahead. Light can loop around compact objects, producing repeated images. The exact view depends on the wormhole metric, rotation, surrounding plasma, and where the light sources are located. A mouth might show an ordinary-looking star field at its center, with concentric, warped copies around it. The transition could resemble walking through a lens that rearranges the entire sky.
And clocks?
Clocks always deserve attention in relativity. If the two mouths sit in different gravitational fields or move differently, their elapsed times can diverge. Locally, your watch behaves normally. But when compared with clocks outside, the mouths may no longer agree. That difference turns a spatial shortcut into something more dangerous, a possible route between different times.
So even the ideal road across the galaxy can become a time machine.
And causality is where the universe may finally refuse the permit.
From shortcut to time machine. How does moving one mouth create a time machine?
Imagine two wormhole mouths initially synchronized. Leave one on Earth and take the other on a high-speed journey, then bring it back. Special relativity tells us that the traveling mouth experiences less elapsed time than the one that remained behind. Alternatively, place one mouth deep in a strong gravitational field, where gravitational time dilation makes its clock run differently. If the wormhole's interior connection preserves the mouth's original relationship, stepping through could carry you from one external time to another.
You could enter one mouth today and exit yesterday?
In the idealized construction, you could create a closed time-like curve, a path through space-time that returns to its own past. But there are limitations. You generally cannot travel to a time before the time shift was created, or before the wormhole existed. And more importantly, we do not know whether quantum physics permits the arrangement to remain stable.
This is where the grandfather paradox enters. If I change the event that led me to enter the wormhole, how did I make the trip?
Yes, relativity can contain mathematical spacetimes with closed time-like curves, but their physical status is unsettled. Stephen Hawking proposed the chronology protection conjecture. Perhaps the laws of physics prevent macroscopic time machines from forming. Quantum fluctuations might grow without bound near the moment a closed, time-like curve would appear, destroying the configuration. That remains a conjecture rather than a completed theorem covering every scenario.
Could consistency save the timeline instead?
Some ideas say only self-consistent histories occur. You can participate in the past, but cannot create a contradiction. Other interpretations invoke branching quantum histories. Those are fascinating, but they move beyond what experiment has established. Wormholes make the causality problem vivid because the geometry itself, not a magical machine, creates the loop.
And if a traversable wormhole can so easily threaten cause and effect, that may be evidence that some hidden principle forbids it.
Possibly. Morris, Thorne, and Yurtsever explicitly connected traversable wormholes with time machines and the weak energy condition in 1988. The result was not an instruction manual. It was a warning. If nature lets you build one kind of exotic geometry, it may also let you endanger causality. Therefore, whatever prevents time machines may also constrain wormholes.
The shortcut asks the universe to let two distant points become neighbors. The time machine asks two different moments to become neighbors.
And we do not yet know whether spacetime has a rule that says some neighbors must never meet.
The quantum computer wormhole. Now we reach the headline that convinced many people a wormhole had already been created. In 2022, a team reported traversable wormhole dynamics on a quantum processor. What actually happened?
The researchers programmed a 9-qubit quantum processor to simulate a highly simplified quantum system with a holographic gravitational description. They prepared two entangled systems and used a teleportation-like protocol. Information inserted into one side later emerged from the other with behavior-matching features expected from a theoretical traversable wormhole model.
Did any physical tunnel open inside the chip?
No. A human, atom, or photon did not travel through a newly created hole in laboratory space-time. The processor implemented quantum dynamics mathematically related through holographic duality to a toy model of gravity containing a traversable wormhole. Calling it a wormhole experiment is defensible within that technical context. Saying scientists opened a physical portal is false.
Why was the experiment important if it was a simulation?
Because quantum gravity is extraordinarily difficult to test. The holographic principle suggests that a gravitational theory in a higher dimensional space-time can be equivalent to a quantum theory without gravity on a lower dimensional boundary. If that correspondence is exact in the models being studied, manipulating the quantum system gives physicists a laboratory language for exploring gravitational ideas. It is like studying fluid behavior with a carefully designed analog. Except here, the relationship between information and geometry may be much deeper.
And this connects to the phrase ER equals EPR?
Yes. ER refers to Einstein-Rosen bridges. EPR refers to Einstein, Podolsky, and Rosen's famous discussion of quantum entanglement. In 2013, Juan Maldacena and Leonard Susskind proposed that entanglement and wormhole-like geometric connections might be two descriptions of related underlying physics. The slogan does not mean every pair of entangled particles contains a tiny tunnel you can fly through. It suggests that space-time connectivity and quantum entanglement may be intimately linked in a quantum theory of gravity.
Then Gao, Jefferies, and Wall found a way to make a holographic wormhole traversable?
In a specific anti-de Sitter setup, they coupled the two boundary systems. The interaction generated negative average null energy in the gravitational description, allowing a signal to pass through the bridge. Crucially, the construction did not allow causality violation. The later processor experiment modeled aspects of that story.
So the honest headline is not, "We made a portal." It is, "We used controllable quantum matter to test a relationship between teleportation, entanglement, and an emergent gravitational description."
Exactly. Less cinematic, perhaps, but conceptually astonishing. The experiment hints that geometry might emerge from patterns of quantum information. In that sense, the deepest wormhole story may not be about transportation at all. It may be about what space is made of.
How would we recognize a cosmic wormhole? If a wormhole exists naturally somewhere in the universe, how would astronomers find it? We cannot simply wait for a spaceship to emerge.
We would look for gravity's fingerprints. A compact wormhole could bend light, influence nearby orbits, produce a shadow-like image, interact with surrounding gas, or affect gravitational waves. The challenge is degeneracy. Many exotic compact objects can imitate a black hole from far away.
Let's start with gravitational lensing.
Any sufficiently curved spacetime deflects light. A wormhole might produce multiple images, rings, unusual brightness patterns, or light arriving from sources on the other side of the throat. The exact signature depends on the model. Recent theoretical studies explore how hotspots orbiting near a wormhole would appear, how images could be confined relative to a critical curve, and how extra peaks might appear in a light curve when photons traverse the throat. Other work studies strong lensing near wormhole photon spheres.
But a strange ring is not automatically a wormhole.
Correct. Plasma, black hole spin, viewing angle, and ordinary astrophysical structure can all change an image. The Event Horizon Telescope's observations give us tests of compact object geometry, but no EHT image has established a wormhole. Researchers can use observations of M87 star or Sagittarius A star to constrain particular wormhole models. A constraint is not a detection.
What about objects orbiting the candidate?
Their orbital frequencies and precession depend on the surrounding metric. Gas in an accretion disk produces X-ray spectra and quasi-periodic oscillations. A wormhole model may predict patterns slightly different from those of a Kerr black hole. We can compare those predictions with data, but astrophysical environments are messy, and models contain uncertainties.
Could gravitational waves expose one?
Possibly. The inspiral and merger of compact objects encode their structure in the waveform. Some exotic compact objects might produce late-time features, informally called echoes, or different tidal responses, or altered ring-down modes. None has yielded a confirmed wormhole. Claims of exotic signatures require extraordinary statistical care because detector noise and incomplete models can create seductive patterns.
So a real discovery would need several independent clues agreeing.
Ideally, yes. An unusual lensing pattern, orbital behavior inconsistent with a black hole, a shadow or emission structure predicted by a specific wormhole geometry, and repeatable observations across instruments. Even then, scientists would compare neutron stars, boson stars, gravastars, plasma effects, and modified gravity alternatives. Wormhole would be near the end of the elimination process. not the first label attached to an anomaly.
Nature does not put a sign over the mouth saying, "Shortcut this way."
And science should distrust anyone who paints the sign before measuring the doorway.
Could wormholes form naturally? Even if the equations allow wormholes, where would one come from?
That is one of the hardest questions. An eternal mathematical solution can be specified as a complete spacetime. But the real universe evolves from earlier conditions. We need a formation mechanism. Could the early universe have produced microscopic wormholes through quantum fluctuations? Could some survive cosmic expansion? Could exotic fields or extra dimensions support larger ones? These ideas have been studied, but none is confirmed.
Could an advanced civilization build one?
The thought experiment usually assumes access to a microscopic wormhole, then asks whether it could be enlarged and stabilized. We have no evidence that microscopic, traversable wormholes exist, no technique for capturing one, and no demonstrated source of the required negative energy. The gulf between a solution and an engineering project is enormous.
Could black holes be modified into wormholes?
Some theoretical constructions join regions of spacetime by cutting and pasting geometries, creating thin shell wormholes. Others use charged or rotating solutions, scalar fields, quantum effects, or theories beyond general relativity. But an observed black hole does not become a traversable wormhole simply because an equation has a second extension. NASA's public guidance emphasizes that black holes are not wormholes. Once inside an astrophysical black hole event horizon, no ordinary escape route is available.
The universe has made black holes in abundance, it seems. Less generous with exits.
Black holes form naturally when matter collapses. Their horizons are dynamically robust predictions, and we observe powerful evidence for compact objects behaving exactly that way. A traversable wormhole needs the collapse to be avoided or counteracted by unusual stresses. Nature tends to close the passage.
What would change your mind? What observation would make you say, "This might truly be a wormhole"?
I would want a compact object whose gravitational effects could not be reconciled with a black hole or other known object, plus a signature suggesting transmission through a throat. Imagine identifying light or matter whose source is geometrically impossible on our side, but consistently appears through the object, with timing, spectrum, and lensing all matching a traversable metric. Or imagine sending a probe toward one mouth and receiving an authenticated signal from a distant region with no ordinary path.
That would be the ultimate confirmation.
Yes, after eliminating fraud, instrumental errors, conventional gravitational lensing, and every other explanation. Until then, the correct status is simple: theoretically rich, observationally unconfirmed.
Why study something we may never find? Some listeners may wonder why brilliant people spend decades studying an object that may not exist.
Because impossible-looking objects are stress tests for theories. Wormholes force general relativity to confront quantum field theory. They expose the role of energy conditions. They sharpen questions about causality. They connect black hole interiors with quantum information. Even proving that a class of wormholes cannot exist teaches us which principles protect spacetime.
Like discovering the rules of a game by trying every move the board seems to allow.
Exactly. General relativity is extraordinarily successful, but it is expected to be incomplete because it lacks a full quantum foundation. Near singularities, inside black holes, and at the earliest moments of the universe, we need quantum gravity. Wormholes provide models where information, geometry, and causality collide.
And perhaps the popular fascination is not only about arriving somewhere faster.
I think it is about refusing separation. We look at a galaxy millions of light years away and feel the cruelty of distance. A wormhole says distance may be negotiable. It imagines that two places written far apart on the cosmic map could secretly touch. That is a powerful emotional idea.
It also transforms the universe from a vast wilderness into a house with hidden doors.
Yes, But science gives that metaphor discipline. We cannot confuse desire with evidence. A beautiful possibility earns investigation, not belief. The most honest wonder contains uncertainty.
Then the study of wormholes has already produced something valuable, even if no traveler ever crosses one. It has helped physicists ask whether space-time emerges from entanglement, whether negative energy can be controlled, whether causality protects itself, and how we might distinguish a horizon from a throat.
And it reminds us that real has layers. The equations are real. The scientific questions are real. The quantum simulation is real. The physical tunnel remains hypothetical. Keeping those layers separate does not drain away the mystery. It reveals where the mystery actually lives.
So, have we finally found a real wormhole? No. Not in the sky, not in a laboratory, and not inside a quantum chip. What we have found is a trail of increasingly precise questions. Einstein and Rosen found a bridge hidden in the mathematics of gravity, but it could not be crossed. Morris and Thorne described what a traversable passage would demand, only to uncover the price of exotic stress and negative energy. Quantum theorists found relationships between entanglement, teleportation, and emergent geometry. Astronomers are learning what shadows, lenses, or gravitational waves might betray an exotic compact object.
And every step reduces the space in which fantasy can hide, while expanding the space in which genuine discovery can occur. We now know that a black hole is not automatically a portal. We know a stable, human-scale throat is an extreme physical demand. We know that a simulated wormhole and a space-time tunnel are not the same thing. We also know our present theories may be fragments of a deeper description, in which information and geometry are two sides of one structure.
Perhaps that is the strange gift of the wormhole. It offers a shortcut across the universe, but forces science to take the longest route. Define every word, test every assumption, and refuse to leap over missing evidence.
If nature has built one, it will not be confirmed by a dramatic headline. It will be confirmed slowly, by light curves, orbital measurements, spectra, waveforms, independent telescopes, skeptical teams, and predictions that survive every attempt to break them.
And if that day comes, the discovery will be larger than a new object. It will mean space-time has architecture we have never touched, that the map of the universe contains connections invisible from the outside, and that distance itself is not as fundamental as it seems.
Until then, the doorway remains in the equations. Closed, perhaps, but still teaching us how to look.
Closing pause. Thank you for joining us inside the Midnight Museum. Tonight we learned that wormholes are permitted geometries, not confirmed cosmic tunnels. That traversability demands extraordinary control over gravity and energy. That time travel may turn a shortcut into a threat to causality. And that the famous quantum computer experiment simulated wormhole dynamics without opening a portal.
Thank you, Alex. The best mysteries are the ones that become more fascinating when we remove the exaggeration.
If you enjoyed this conversation, share it with someone who still thinks every black hole leads somewhere else. Tell us in the comments, if a safe wormhole opened tomorrow, where or when would you go? Subscribe for more late-night journeys through history, science, and the hidden architecture of reality. Until the next door opens, keep asking careful questions, keep looking into the dark, and good night. Estimated spoken length, approximately 45 minutes at a calm two-person podcast pace, including pauses and performance beats.